Before we proceed to the special lecture, I would like to introduce our speakers today. The first speaker is Professor Dr. Roshankar Narasinghe, or Professor Lodge. He is the Executive Chair in Climate Change Impacts and Coastal Lit at the Department of Coastal, Urban Risk and Resilience of IHE Delft, and at the Department of Water Engineering and Management, University of Twente, Netherlands. He is also a senior specialist at Harbor, Coastal and Offshore Department at Delft, Netherlands, and holds an honorary professor position at the University of Melbourne, Australia. In addition, Professor Lodge is coordinating lead author and contributing author in the IPCC Special Report on Oceans and Cryosphere in a Changing Climate. And the second speaker is Kin Navarat. She is a PhD candidate at the Coastal and Urban Risk and Resilience Department under Coastal System and Engineering and Port Development Share Group. Kin obtained her bachelor and master's degrees from Myanmar Maritime University with the specialization of port and harbor engineering. She received another master's degree in coastal engineering and port development from IHE Delft. As her graduation research, she estimated the coastal flood risk of European critical infrastructure under current and future climate scenarios, which involves a continental scale geospatial data, handling and parallel processing. Ladies and gentlemen, may I have the honor to invite Professor Lodge and Kin give us a special lecture. Please welcome. ขอเสียงปรบมือด้วยค่ะ
Good afternoon. It's really nice to be back here again. And thank you for all the hosting organizations for hosting this. And especially my good friend Sutat for always being so welcoming and a very nice lunch, Sutat. Thank you. So it's really nice to see such a big crowd. This presentation is, well, really the main results will be presented by Kin later. That's coming out of the PhD work she's doing. But what I speak about will be more the setting for it that came from the IPCC report that we published recently. So as the MC stated, so these are all the different roles I played in the AR6. This takes a little bit a while. Okay. The pointer? Good. Yeah, okay. So these are all the different roles I played in the IPCC AR6 report. My main role was as coordinating lead author of chapter 12, which looked at the regional climate change. And then I was also lead author in summary for policymakers and technical summary and contributing author in several other chapters. The background for what Kin studies is extreme sea levels for different global warming levels all around the world, and here she will present some results for Thailand. Now, for the background, I will talk more about what we found in IPCC. So now it doesn't go. Okay, got it. Okay. So the broader project, as I said, is about extreme sea levels and coastal flooding at global scale under different global warming levels. So this is different to the previous studies that have been done before because of this mainly, under different global warming levels. most of the previous studies have been, or all the previous studies have been done for different climate scenarios, but here we are looking at different global warming levels. And that's a completely different way of looking at things. And the funding for this project, for this work, comes from two main sources, from AXA Insurance in France and the Dutch Ministry of Foreign Affairs, through an internal collaboration we have. Just thought I'll mention that. So to start off, I think we should define what we mean by extreme sea level, because there are different definitions for extreme sea level. So what we define is exactly as it is defined in the AR6, IPCC AR6, in chapter 9. So that is the combination of tide, storm surge, wave setup, and for the future also sea level rise. So that's remember that definition, because some people also just call the storm surge as the extreme sea level. Yeah, get closer. Okay. But our definition throughout this presentation will be all of these together. So one of the headline statements that we made after all our assessment in AR6 Working Group 1 is pretty alarming. It's that the global mean sea level rise is projected to turn what today is a 1 in 100 year extreme sea level event into an event that would occur multiple times a year by the end of this century. So an event that would be as rare as 1 in 100 years would become an event that could happen more than once a year by the end of this century, and we have high confidence in this. So this is what drove. So one of the headline statements that we made after all our assessment in AR6 Working Group 1 is pretty alarming. It's that the global mean sea level rise is projected to turn what today is a 1 in 100 year extreme sea level event into an event that would occur multiple times a year by the end of this century. So an event that would be as rare as 1 in 100 years would become an event that could happen more than once a year by the end of this century, and we have high confidence in this. So this is what drove us to look into this in more detail. Now a little bit about the assessment report itself, for those of you who are not very aware of it. So the IPCC 6 assessment report also comprises the 3 traditional working groups that all IPCC reports before this one had. So the working group 1, which is the one that I was involved in, that's dealing with the physical science, and working group 2 is more on adaptation, working group 3 is in mitigation, and it will end up with synthesis report, which will be released, I think, in a couple of weeks' time. So this is the timeline. Working group 1 was released in August 2021, and working group 2 and 3 were released last year, and synthesis report is expected to be released very soon. How the IPCC chapters or the process is structured is something like this. So at the top we have the IPCC Bureau. These are nominated people from all over the world, about 10 people altogether, 12 people. And then we have a technical support unit called TSU that helps with all the, setting up the meetings, the agendas, and also important things like making, they manage the whole practical side of things for us scientists to deal with it. And then we have 3 working groups, working group 1, 2, and 3. And in each working group, you will have a certain number of chapters. So in our working group, in working group 1, there were 13 chapters. And each of the chapters will have 2 to 3 coordinating lead authors. So I was one of them for chapter 12. And each chapter will also have about 10 to 15 lead authors. And then we have a couple of chapter scientists who really help us a lot with the figures and the references and all. They really do a lot of work. And these are generally postdoc level people. So people who already have a PhD, but are younger people. They need to be young because they need to have a lot of energy to stay late nights and work weekends and stuff like that. But without them, we couldn't do anything, really. They really are a very important part of the team. And then we also ask contributing authors to provide, let's say, a paragraph or a figure or some specific help for certain things. So that was a very interesting and very time-consuming adventure for those 4 years. So this is just to show you a team. So this is the working group 1 author team. This many people are involved in one working group. So this is our team. We had 31 coordinating lead authors, 167 lead authors, review editors, chapter scientists, and more than 500 contributing authors. So these 3 categories, coordinating lead authors, and review editors, are basically nominated by countries. Or some are invited directly by the IPCC, but most are nominated by countries. And we then invite chapter scientists and contributing authors. So that's a little bit about IPCC, how that works. Now in AR6 was a little bit different to the previous ARs. We defined new climate scenarios. So if you know about the AR5, in the AR5 we had RCPs, or reference concentration pathways. In AR6 we have SSPs, which are shared socioeconomic pathways. So these are the 5 that we followed. The SSP 11.9, 12.6, 24.5, 370, and 58.5. So here, just to show you the pathway, is the way the carbon dioxide concentration in the atmosphere is expected to vary through the 21st century. So if you look at the most optimistic scenario, which is 1.9, the light blue line, then according to that scenario, we are already cutting down emissions fairly radically, and we will reach net zero by about 2050. The next optimistic one is SSP 12.6. Also, we start to cut down emissions already slowly, and then we reach net zero about 2080. This is a more moderate scenario where we keep increasing in emissions until about 2050 and then start to drop. And 3.70 is a brand new scenario that we introduced in AR6. That we introduced because that's what we are kind of tracking now. So if we don't do any changes now, keep going as we are going, this is the climate scenario that we will end up in. 58.5 is very similar to RCP 8.5 in AR5. So that's where we really accelerate even our emissions, and it's a really worst case scenario which keeps going up radically until the end of the century and then flattens out. So these are the 5 scenarios that we followed throughout AR6. And here I also have the figures for other contributors to greenhouse emissions. So carbon dioxide is not just to show that carbon dioxide is not the only greenhouse gas. So there are also these other things like methane, nitrous oxide, and sulfur dioxide, which are dangerous in another way, because these are what we call long-lived gases. So carbon dioxide actually, it's not a long-lived gas. It's in the atmosphere, but if we do the right thing, we can also get rid of it quite fast. But these guys, once they are in the atmosphere, they stay a long time. So they are actually quite dangerous. Now, a little bit about temperature projections for these 5 scenarios. So these are the 5 scenarios I mentioned. And here, if you concentrate on the first bar, that is the total projected warming that is projected by the end of this century relative to the pre-industrial period. Okay? So by the end of this century, relative to 1850, 1900. And the dark bit in this first bar, in every figure you will notice is the same. Yeah? It's about 1.1 degrees. So that to show that's where we are now. The world is now 1.1 degrees warmer than it was in 1850. So that's our current situation. And then the total height of these bars is the temperature, the global mean temperature that we are expected to reach if we follow these lines, if they follow these scenarios. So by this really optimistic scenario, 1.9, we stay below 1.5, which is what we would like to achieve. In this other optimistic scenario, we get close to 2 degrees. And if we keep going as we are going now without making any changes, we get up to 3.5 degrees or a little bit higher. And this really worst case scenario, we get up to even 4.5 degrees. So these numbers may sound small, like 3.5 degrees, you may think, okay, well, if 30 degrees and 33.5 degrees is the same for me, it's no big deal. But it is a big deal, because every fraction of a degree that the temperature increases, lots of things that maybe we as humans can handle personally, but other things cannot handle these things, such as the species, certain species can be lost. And also with every fraction of degree of warming, the extreme events, the frequency of extreme events are projected to increase rapidly, like the things that Kin will talk about. Not only extreme sea levels, but extreme precipitations and extreme heat events, all those things. Something that happens once in 10 years today could happen every day or with a certain amount of warming. So even 0.5 degrees or 1 degree is actually quite a big increase when you think of it like that. So this was just to give you an idea of the temperatures that we could expect to reach if we follow these different climate scenarios. And now to go into sea level rise, because this is what is really underlying the extreme sea level changes. So all the sea level rise projections in AR6 are given in chapter 9 of the report. This is the full author list here. So the projections for sea level rise given in AR6 are a little bit different. We again, not only because scenarios, but we also give projections up to 2300. But first, this figure is in the summary for policymakers. This gives projections up to 2100, like all the other ARs. So this figure shows the global mean sea level change relative to 1900 and up to the end of the century for the 5 different scenarios. So you can see here the figure gives these values are relative to 1900. But if you want to then convert into a more recent baseline, like let's say the end of the last century, then you have to subtract 0.16 from these numbers that are given here. But in the text, the values are given relative to 1995, 2014. So you can see even if we keep going as we are going now with SSP 370, we can reach about 1 meter of sea level rise. And we also have this dotted line, which is new to IPCC. So that is what we call a low likelihood, high impact storyline. It's not a scenario, it's a storyline. So why that is different is that, so these are all plausible scenarios of shared socioeconomic pathways. Storyline means if a number of things happen at the same time, then that's where we can end up. So that's an illustration of kind of what can happen if certain things happen all together. So for this dotted line to occur, we will first need to have SSP 58.5. Now SSP 58.5 is looking increasingly unrealistic. Recent research shows that because of the cuts that governments have made since the Paris Agreement in 2015, we are probably not going to get that far. So that's good news. We probably will not reach SSP 58.5. So for this storyline to happen, we need to have SSP 58.5 happening, and then we also need to have much faster than projected disintegration of ice shelves. We need to have ice cliff collapses in Antarctica, and we need to have larger than projected mass loss in Greenland. So if all these things happen, then we can end up with this line. And that reaches about 1.76 meters relative to the year 1900. Now I said earlier that we also provide sea level projections 2300. So this is the earlier figure I showed, plotted on the same scale. These are the projections for two scenarios until 2300. So you can see here with the 2.6, which is an optimistic scenario, we can get up to 3 meters of sea level rise. And this is the worst case scenario of 8.5, we can get almost to 7 meters of sea level rise. These are pretty big numbers by 2300. And considering that low likelihood, high impact scenario where all the Antarctic ice shelf collapses and Greenland collapses, then we also see that sea level rise exceeding 15 meters cannot be ruled out with these deeply uncertain situations. But it remains deeply uncertain. So, then another conclusion we made in AR6, a high-level conclusion, is that relative sea level rise contributes to increases in the frequency and severity of coastal flooding and to coastal erosion along sandy coasts. We also have high confidence in this. Now, high confidence in IPCC language has a specific meaning. Okay? It's not something that we kind of put out of the air. So high confidence means we look at different lines of evidence, so it could be past observations, it could be attribution studies, it could be projections, and many papers say the same things, then we have high confidence. If we have only, past observations showing some trend and the future projections showing a different trend, then we will not have high confidence. And if we have like only 1 or 2 papers saying the same thing, also we will not have high confidence. So when we have high confidence, that really means we do have high confidence. So we debate, actually we would debate about some things for days about this, whether to come up with medium confidence or high confidence. So going into those coastal flooding and coastal erosion things now, we all know Thailand, like being a coastal country and also a country that relies heavily on port infrastructure and coastal tourism. I don't have to tell you these things, but sea level rise will have major implications on low-lying coastal zones all over the world, which is now almost home to 700 million people now, and projections show that it will rise to about 1 billion by 2050. So that's low elevation coastal zone. That's the definition of is the area below 10 meters above mean sea level, and it produces about 14% of the global GDP. There's a lot of critical infrastructure, heritage sites. So it's a very important part of the world. But importantly, so decisions with time horizons of decades to over a century are being made now. So if you want to plan the laying of coastal railway lines or highways or whatever, sanitation plants, wastewater treatment plants, airports, these have a very long life cycle, 100 years, 50, 100 years. And where to locate these things, the decisions are being made now for something that is expected to last. The business case is made for these, thinking that it has a lifespan of 50 to 100 years. So then we need to take into account climate change in making these decisions. We can't just make these decisions based on what we have seen in the past. So realizing this, AR6 provides a regional assessment of key coastal climatic impact drivers, because the previous ARs gave very global kind of results. So global average values or global maps that's based on global scale assessments. But for regional decisions, then we need higher resolution information of how things will change in a local area. Now, IPCC, still being an international assessment, we can't go into the level of countries. But we tried this time to go into at least to a regional level granularity where we divided the world into, I think, 44 different regions. So for example, I think all of Asia is divided into 10 or 12 sub-regions. I can't remember exactly now. So we reached an unprecedented level of granularity this time, but still for country level or local decisions, then we still need to do local scale assessments. But these can be used, the IPCC assessments can be used to get a first idea of which are the hotspot regions where changes can be expected. So in terms of coastal climatic impact drivers then, in this regional assessment, which is the chapter that I was coordinating lead author in, we looked at 3 specific climatic impact drivers or CIDs. Relative sea level rise, which is different to global mean sea level rise. Relative sea level rise will also take into account more regional effects such as subsidence, for example, as much as it is possible in the given literature. And we looked at coastal flooding and coastal erosion. So these are 3 main CIDs that we looked at in working group 1. So this is the granularity I mentioned. So this is how we divided up the whole world, right? So all the continents are divided into 44 regions. And in the report, we give observations and projections of the direction and magnitude of change for 33 different climatic impact drivers in each of these regions. And we cover all these continents. So Africa, Asia, Australasia, all those. Now, this figure is also from the summary for policymakers. I don't want to go into details of this, but these are the 33 different climatic impact drivers or CIDs we looked at on this axis. And here on the y-axis shows the number of regions each of these CIDs are projected to change. Above 0 are increases and below 0 are decreases. And the dark purple are regions with high confidence of increase. Now here are the coastal CIDs. You can see coastal flooding here, where I have drawn a box around, is projected to increase in most of the regions of the world. Okay, so that's why this is a matter to look at urgently, because in most of the world's regions, coastal flooding is projected to increase with high confidence. And what we reported in the AR6 chapter 12 is summarized in this figure. So we gave these projections of extreme sea level for 4.5 and 8.5 end of century and mid-century. And the main summary statement we come up with is that in a globally average sense, the 1 in 100 year extreme sea level is projected to become an event that occurs multiple times under RCP 8.5, while under RCP 4.5, it's projected to become 1 in 5 year event. So that still means that we can gain a lot by mitigation. If we stop at 4.5, then going to 8.5, we can get an event that is happening once every 5 years as opposed to an event that happens many times a year. It's not good, but it's better than not doing anything. Now, I will go into this a little bit. I want to show you something that we made at IHE. So how do we exit and go into the internet then? Can you do that? So we used a lot of data sets in the IPCC assessment, and there was no one place that everything was there together. So we made an online viewer where we brought all those data sets into one platform. I think I will have to drive it from here. So the data sets that we use for regional sea level change, extreme sea level, coastal flooding, shoreline change, and extreme waves in this one website. Mind you, these are all global data sets, so you can still get a good idea of how things are expected to change regionally, but I wouldn't use these projections that are given here for exact site-specific calculations. For those, you will need to do serious detailed modeling. So let's take one example just to show you how this works. We go to the page. No? Ah, yeah, it's a bit slow. Disconnect. Okay, so when you click on the dataset, you get a page like this. Then you can select. There are several datasets here for extreme sea level. These are all published. So we made a decision in COFU. We only put published datasets that are freely available. So if you go to the first dataset, this is. Then we give the reference also. So this is from this paper by Vustukas et al. So then we have a baseline, let's say a 100-year return period or 1-year return period or 10-year return period. You can select what you want to select and view. And instructions are given here on how to use it. So basically each of these, if you zoom out, you see a number of points with a number in it. So that means basically the number of data points that are inside each of these circles. But when you zoom in, you see they separate into individual values, right? So if you want to look at Thailand, let's say somewhere here, if you hover over it, you actually get the projection value for the baseline for 10-year return period. Okay, you can also look at RCP 4.5, 2050 or 2100. You can increase the return period to 100 years. Is it still working or is it done? Oh, it's working. Well, it works much faster than this back in Holland. Well, it's interesting. Actually, good. We have to do something about that. Has any of you here tried this tool before? Yes? No? Sound like. Well, I don't know whether it's a temporary situation now or, but because this should really not be taking this long. Well, anyway, all that you would have seen are different colored circles with different values. So, but try this for whatever you are interested in, and if it is actually always really slow, then let us know. We can do something about increasing the speed. When we try it in Holland, it's instantaneous, very fast. Okay, so I'll get out of this one, go back to the presentation. Yes, next. Here's my thing. Okay. Right. So that's COFU. Yeah, one thing is we have not enabled data downloads here. But if you need any data, then just send us an email and we will provide it to you. So, projections by climate scenario versus global warming level. I mentioned this at the beginning of my presentation. The projections by scenario, such as RCPs or SSPs, are geared more towards adaptation because it follows a certain timeline, right? So even the SSPs I showed you earlier, on the x-axis was the time. So it's about how carbon dioxide concentrations will change over time. So then when you look at how, let's say, extreme sea level or coastal flooding or anything will change along a climate scenario, it gives you an idea about how the hazard will change in time by mid-century or end century. So they are used more for adaptation. Projections by global warming levels, so that's like a projection of how something will change with a warming level of, let's say, 1.5 degrees more than pre-industrial or 3 degrees more than pre-industrial, are useful for mitigation as well as for adaptation. So especially the mitigation decisions like the Paris Agreement or at the various COPs, the high-level decision makers try to agree on what is the temperature target that the world should reach. Is 1.5 degrees or 2.5 degrees or 3 degrees or what? So that's why actually most of the projections that we assessed in AR6 were by global warming level. So almost, well, all the CIDs that were assessed were available by global warming level and scenario, except the coastal CIDs, which were only available by climate scenario at the time of AR6. We did not have any projections of coastal CIDs by global warming level. So that's why we decided to do that after AR6 was published. Of course, we didn't have that. In IPCC assessments, we don't do really original research. We are not supposed to do original research. We assess what's published already. So that's a gap that we found. And as kind of the person who everyone turned to for coastal CIDs was me. And it was, became very clear to me that in the coastal field, we have been focusing so much on adaptation and not so much on mitigation. So that's why we thought, okay, we have to fix this. And so I will leave it now for Kim to talk about what she's doing in terms of global warming levels and extreme sea level rise. Thank you.
Thank you, Professor Roche. Good afternoon. Sawadika. Nice to meet you, all of you here. And my name is Kin Nawarat. Today I will be presenting about extreme sea level projections for Thailand under different global warming levels. I am a PhD candidate of Coastal and Urban Risks and Resilience Department at IHE Delft. Before I start my presentation, I would like to introduce myself a little bit. I came from Myanmar, which is one of the neighboring countries from Thailand, and we share a very long border, so we have similar culture, and I already feel like home coming to here. And I got my bachelor and master degrees from Myanmar Maritime University with the specializations of port and harbor engineering major. And I got a full scholarship to do another master at IHE Delft. And for my master thesis, I assess European critical infrastructure at risk from coastal flooding due to extreme sea levels, which is a large-scale assessment, and Professor Roche was my supervisor for this large-scale assessment. And after my master, I decided to continue doing my PhD and work together with Professor Roche on the topic of extreme sea levels, especially the climate change effect on it. My PhD were mainly involved in detecting extreme sea level trends over time, and I will also observe we humans are responsible for that change in extreme. The slide's not, oh yes. Before I present my results for Thailand, I would like to start with the paper which released after IPCC latest report AR6. Tibaldi et al. Published a paper in 2021, which is called Extreme Sea Levels at Different Global Warming Levels. And Professor Roche was one of the co-authors. This, I also estimated the extreme sea level projections for Thailand by following the methodology from this paper. So if you want to know more about methodology, you can always refer to this paper, which is publicly available online. And this paper is unique because we have a few extreme sea level projections, which is by emission scenarios. And this paper is the first global study of extreme sea level projections by warming levels. In the paper, 3 extreme sea level data sets, which is for present day, are combined with 2 sea level projection data sets. But the papers focus only on 100-year return period, especially how these 110-year return period extreme sea level will change in terms of their frequency and different warming levels. And the paper considered not only the warming levels of 1.5 degrees Celsius, but also the very optimistic 5 degrees Celsius. And we expand the paper analysis. The slide should be moving. Yeah, we expand the paper's analysis to include a broader range of extreme sea level return periods for Thailand. And we see how other return periods are changing. And if the global temperature rises to 1.5 degree, 3 degree, and 5 degree relative to the pre-industrial period. But I would like to explain about why we chose specifically these warming levels and these return periods. Not working again. Oh yes. We chose 1.5 degree because it is what we are trying to achieve as globally according to 2015 Paris Agreement. And 3 degrees Celsius is what we actually currently headed for, and 5 degrees Celsius is a plausible worst case scenario. And we chose these return periods because 1 year and 10-year return periods are commonly used in coastal zone management for storm erosion. And we use 50-year return period to design port and harbor infrastructure. And we use 100-year return period for coastal setback line definition. And insurance company use 200-year return period to calculate their insurance premium. That's why we consider these return periods and these warming levels to be practical in real-life applications for Thailand. Thank you. Before I start presenting the results for Thailand, I would like to explain return periods and our common misunderstandings. This is to avoid any misinterpretation in our results. When we say 10-year event, if we change it into probability, 1 by 10 is 0.1, and multiplying it with 100, and that means we have 10% chance that 10-year extreme sea level will be exceeded in any 1 year. And if we say 50 years, that means we have 2% chance that 50-year level can be exceeded in any 1 year. And if we say 100-year event, we have only 1% chance that level can be exceeded in any 1 year. So 100-year event does not mean that that event will happen regularly every 100 years, or it also does not mean that, I think we both click. It also does not mean that that event will happen only once in 100 years. Also, another thing we should keep in mind with return period is the higher the values of the return period, we have less chance of that event can happen, but we have very high impact if they really happen. Now, I would like to start presenting about the results for Thailand. First, I would like to start with how 100-year return periods will change under different global warming levels. This is the map for present-day 100-year extreme sea level along the Thailand coastline. To be able to cover the whole coastline of Thailand, we chose these locations. For the southern part, we have Phuket, Songkhla, Surat Thani, and at the northern part of the Gulf, we have Phetchaburi, Samut Prakan, Chonburi, Rayong, and Chantaburi. And here is the color bars to see how the intensifications of the extreme sea level. And 0 to 1 meter we present with green, and 1 to 2 with a little bit green and yellowish color, and 2 to 3 meter is with yellow, and 3 to 4 is in orange, and greater than 4 meter is more red. And at each location we can see that we have 3 cycles because we want to include uncertainty in the future in our results. We cannot exactly predict the future with a number. And we have these data sets for current extreme sea level, which came from different methods and different models, so they have uncertainties. And also in the relative sea level rise for the future, we have uncertainties. So at each location, to cover all these uncertainties, we have 3 estimates. The upper cycle represent the pessimistic estimate, and the lower cycle represent the optimistic estimate, and the cycle in between represent the value in between, the central estimate. As we can see, if we just look into the center cycles around the coastline, for present-day extreme sea level, we have from 0 to probably around 1.5 meter for present day. And this is the map for if the global temperature rises to 1.5 degree relative to the pre-industrial period, we will, all the extreme sea levels, present 100-year extreme sea level along the Thailand coastline will change, because we can see the colors become more yellow, which means it becomes more than 1.5, but not up to 3 meter yet. And if the warming level changes, increases to 3 degree, yeah, and the colors becomes more intensified. And for the 5 degree, we have more red, which means it's more than 4 meter. So from this slide, we can really see that with increasing warming level, we have increasing 100-year return period extreme sea levels. So to be able to analyze the results, in detail, we also present the result, the changes in percentage. So for each location, we calculated their changes in percentage for 100-year return period for different global warming levels. So on the x-axis, we have different warming degrees, 1.5, 2, 2.5, 3, 3.5, and 5. And on the y-axis, we have the change in percentage. Y-axis are the percentage value. And we use the same scale of x-axis and y-axis so that we can also compare across the locations. And here we also consider the uncertainties. So as you can see, all the red dots, they represent pessimistic values. And the green color represent the optimistic value. And the orange is the central estimate. So let's look at together a place, Chonburi, for example. And for 1.5 degree, we were forget about optimistic and pessimistic, and we will just follow the value in between the orange cycles for the purpose of easy interpretation. So for 1.5 degree, this orange cycles is at 60%, which means if the warming degree rises up to 1.5 degree, current day 100-year return period will be increased 60% for Chonburi. And if it is increases up to 5 degree, and then current day value will be increased to about 200%. So this kind of increasing across warming levels can be seen all the locations along Thailand coastline, but Phuket and Songkhla has the greatest percentage change. So at other locations for 1.5 degree, we have about 60% increase, but for Phuket and Songkhla, we have about 75% increase. And if the warming level, if the warming level rises up to 5 degree, other places has about 200 percentage, but Songkhla and Phuket has 240% increase. So we can conclude that these two locations are more sensitive to global warming effect than any other locations for this particular return period, 100 year. And now we looked into the other return periods and 1.5 degrees Celsius of warming level. And again, we have different graphs for each location. And for in the x-axis, this time we have return periods. So from 1 year, 10 year, 50 year, 100 year, and 200 year return periods. And on the y-axis, we have the percentage change. And we have the same scale of x-axis and y-axis so that we can compare across the locations. And also we also include uncertainties, so red pessimistic, green optimistic, and the middle estimate with orange. So let's again look at the Chonburi. We have for 1 year return period will change and 1.5 degree warming scenario up to around, I cannot really see, 80%. And 50 year will be around 60% increase. And for 200 year, we have around 55% change. But we can also see from these graphs that the higher the return period, the changes get smaller. So we have more changes in lower return periods, which we occur frequently but low impact. But this kind of pattern is the same for every locations. But again, for Phuket and Songkhla, the changes are higher. So we can see that for Phuket and Songkhla, not only for the 100-year return period, but also in all return periods, they are quite sensitive to global warming effect than other locations. And this is how all these return periods will change and higher warming level, 3 degrees Celsius. So with 1.5 degrees Celsius, we have this range. With this range is only 20% to 180%. But now under 3 degrees Celsius, we have the range is increased to 50% to 350%. The minimum bound and also the maximum bound of the range increase. And again, we see that the Phuket and Songkhla has higher increase than other locations. And this is under the worst case scenario of global warming, 5 degrees Celsius. And the range becomes 50% and even up to 500% for the current day return period, extreme sea level return periods increase. And again, Phuket and Songkhla are quite sensitive. So to conclude, we would like to deliver a message that extreme sea level all around Thailand will increase by 20% to 180% and 1.5 degree Celsius warming scenario, 50% to 350% and a 3 degree warming scenario, and even up to 50 to 500% and a 5 degrees Celsius warming scenario. And we also observed that extreme sea level increase is higher for low return period extreme sea levels than the higher return period. That means Thailand needs to prepare for adaptation and mitigation plans, not only for the high impacts and low probability events, but also very frequent but low impact return period events. And as we witness from our results, the increase in extreme sea level becomes highly pronounced when the warming level is greater than 3 degrees Celsius. And the extreme sea level increasing trend for increasing warming level is similar all around the country, but the changes are larger along the southern coastline. So, yeah, these are the results and conclusions from our findings. And I would like to start my part of the presentation here. And I would like to invite Professor Roche again to discuss future directions. Thank you so much for your attention. Khop khun krab.
Okay, right. So, thank you. I asked Kin to do this part of this slide also, but she refused. So I will just do that. Actually, these are the same things I said at my last presentation too. So what does this all mean, and what can Thailand do? I see here definitely more organizations than were present in my last presentation, so that's very good. Well, first of all, I think that something that is not there is, I think what ONEP is responsible for. Keep contributing to the global climate mitigation effort. That's a very important thing. In terms of coastal flooding and extreme sea levels, so all the results that I presented and Kin presented, they are coming from global scale assessments, right? So they are global models, and when you run models globally, you have to make some decisions. To enable such large-scale modeling efforts, you have to make some assumptions, you have to cut some corners, so you can't make it work exactly with high accuracy at every single location. So to look at things at a local scale, even at country scale, I think it's very important, especially Thailand being in a monsoon-prone area. You need to do an ensemble downscaling study which selects the global climate models that feed into the downscale models very, very carefully in such a way that the monsoons are represented in those models. Because if the monsoons are not captured in the parent models, no matter how much downscaling you will do, the monsoons will not be there in the downscaling also. So that's an important thing I think Thailand could do. And I definitely know the capacity is here in HII, in other organizations, to do that. So that way you can get more high resolution and more reliable projections at country level. And then for coastal flooding, which is what we are trying to avoid, right? That's one of the main threats of extreme sea levels. You also need, one of the main things that we see is really critical to get good flooding estimates is a DEM. It's a good digital elevation model. The accuracy of the digital elevation model is fundamental to get accurate coastal flood modeling results. So if as a country or if as regions or provinces you can get like LiDAR-based DEMs, that would be really helpful. However accurate your coastal flood modeling, the extreme sea levels and all the flow modeling is, if the DEM is a meter off, then your projections of flooding will be also off. So that's would be a very good investment, and also like really capturing all these flood defenses, natural and artificial flood defenses are very important, because if there's one gap in a flood defense, that's where all the water will flow, right? So whatever dam you use has to be able to capture that, or you have to get the information of the flood defenses and manually enter that into the dam. Like we did a recent study for one event in France, Cynthia, and that's where what we did there. We used a 5-meter resolution DEM, but running the model with a 1-meter resolution DEM was not feasible, so we got information about the flood defenses from the 1-meter resolution DEM, and we put them manually into the 5-meter DEM, and then we ran the flood model, depth 3D, flexible mesh at 10-meter resolution all over, and that was a fairly huge computational effort, but it can be done. So representing flood defenses is really critically important. So in the global studies that I showed you, we don't have that information. We use proxies for that, like the flood defenses are assumed based on GDP and population and things like that. So they are definitely not measured quantities. And then, for a local area, even at country scale, I think we can use now this new model that Delta RS has produced. Swings is very fast, and we can use that to do fully dynamic coastal flood modeling, as opposed to bathtub. A lot of people have been using this bathtub modeling, right? So you say, okay, this is the extreme sea level, everything up to this level is going to be flooded, which could be quite far from the truth. So actually, estimates in Europe have shown that using that bathtub approach can lead to overestimates of about 30% of the flooded area. So it's also good to use fully dynamic coastal flood modeling, and this can be done. So if you use that with a accurate LiDAR-based DEM and your local scale reliable extreme sea levels, you will get a really nice result at local scale that can feed into your adaptation plans. And then once you have that, once you have the flood maps, flood depths, flood extents, then you also have the your development values and infrastructure values. So then you can do a flood damage and risk assessment at a high resolution, and then hopefully make risk-informed adaptation decisions. So I think I will stop there. Yes, adaptation measures you can decide later. And thank you very much. Okay.
Thank you very much indeed, Professor Lodge and Keen, for your informative lecture. We are confident that your expertise would be enrich the knowledge and extend the horizon of all participants. Ladies and gentlemen, may I invite Dr. Piyaman C. Somporn, Director of Hydroinformatics Innovation Division, and Dr. Vinay Chavivat, Researcher of Hydroinformatics Innovation Division, to summarize the lecture contents from Professor Lodge and Keen in Thai for better understanding about the climate change. Please welcome. ขอเสียงปรบมือด้วยค่ะ
ครับสวัสดีครับผมวินัยนะครับผมขออนุญาตเป็นตัวแทนฝ่ายไทยที่จะมาเขาเรียกว่าสรุปนะครับของ Professor Lodge ว่าที่ผ่านมาเนี่ยได้มีการศึกษาอะไรแล้ววันนี้เราได้อะไรบ้างนะครับใน ในประเด็นช่วงแรกๆนะครับทาง Professor Lord ก็ได้กล่าวถึงที่มาของโครงการที่ได้นำเสนอในวันนี้นะครับว่าเป็นโครงการศึกษาระดับน้ำทะเลสุดขั้วน้ำท่วมชายฝั่งที่สเกลระดับโลกนะครับภายใต้อุณหภูมิที่อุ่นขึ้นที่ระดับต่างๆภายใต้โครงการสนับสนุนจาก AXAอิสแลนด์นะครับแล้วก็กระทรวงการต่างประเทศของเนเธอร์แลนด์นะครับผ่านทางโครงการ Water and Development Partnership Program นะครับคราวนี้มาดูในส่วนของนิยามคำว่าระดับน้ำทะเลสุดขั้วคืออะไรนะครับก็ได้ให้คำนิยามว่าเป็นการรวมกันของระดับน้ำขึ้นลงนะครับขึ้นซัดชายฝั่งหรือว่า storm surge นะครับขึ้นยกตัวระดับน้ำทะเลยกตัวนะครับคราวนี้ที่ผ่านมาการศึกษาส่วนใหญ่นะครับก็จะเป็นการศึกษาของระดับน้ำทะเลยกตัวเฉลี่ยนะครับแต่ในวันนี้ที่ได้นำเสนอไปก็จะเป็นในเรื่องของระดับน้ำทะเลสุดขั้วนะครับที่รอบการเกิดที่100 ปีนะครับที่อาจจะเกิดขึ้นหลายครั้งใน1 ปีนะครับที่ระดับความเชื่อมั่นสูงนะครับถัดมาก็จะเป็นในเรื่องของการบรรยายเกี่ยวกับตัวรายงาน AR6 นะครับว่ามีคณะทำงานอยู่หลายคณะนะครับไม่ว่าจะเป็นคณะทำงานในส่วนของการประสานงานในเรื่องของรายงานคณะผู้แต่งแล้วก็นักวิทยาศาสตร์ประจำบทนะครับรวมถึงผู้แต่งร่วมนะครับซึ่งมีความน่าเชื่อถืออยู่ระดับสูงนะครับในการที่เขียนรีพอร์ตฉบับนี้นะครับถัดมาก็จะเป็นในเรื่องของการปลดปล่อยก๊าซเรือนกระจกนะครับก็จะทำให้มีผลต่อการปลดปล่อยก๊าซคาร์บอนไดออกไซด์ทั้งในอดีตและปัจจุบันนะครับโดยที่ผ่านมาการปลดปล่อยก๊าซเรือนกระจกต่างๆเนี่ยก็จะให้แนวโน้มของอุณหภูมิที่สูงขึ้นแตกต่างกันนะครับโดยเฉพาะกรณี SSP 119นะครับ SSP 126และ SSP 245ก็จะมีแนวโน้มที่จะลดลงหลังปี 2050นะครับแต่ในกรณี SSP 370 SSP 585จะมีแนวโน้มการปลดปล่อยก๊าซคาร์บอนไดออกไซด์สูงขึ้นนะครับก็จะทำให้อุณหภูมิสูงขึ้นตามไปด้วยนะครับถัดมาก็จะเป็นการพูดถึงตัวรายงาน AR6 นะครับที่เกี่ยวข้องกับระดับน้ำทะเลไปจนถึงปี 2100 นะครับว่ามีผลกระทบอย่างไรบ้างนะครับผลกระทบที่เกิดขึ้นก็คือตัวที่เกิดขึ้นเนี่ยคือภาวะโลกร้อนในกรณี SSP 585ก็จะส่งผลทำให้การละลายตัวของน้ำแข็งเนี่ยเร็วกว่าปกตินะครับแล้วก็มีการเกิดขึ้นแบบฉับพลันโดยเฉพาะการเกิดความไม่มั่นคงของแผ่นน้ำแข็งแล้วก็ผาน้ำแข็งบริเวณผิวทะเลนะครับบริเวณอาร์กติกแล้วก็มีการสูญเสียมวลเร็วกว่าที่คาดการไว้ที่ประเทศกรีนแลนด์นะครับถัดมาก็จะพูดถึงในเรื่องของผลกระทบที่เกิดขึ้นนะครับโดยเฉพาะพื้นที่ลุ่มต่ำชายฝั่งทะเลนะครับประชากร700 กว่าล้านคนนะครับได้รับผลกระทบเพิ่มเป็น 1,000 ล้านคนในปี 2050 โดยเฉพาะเกาะเล็กๆแล้วก็สามเหลี่ยมปากแม่น้ำมหานครชายฝั่งนะครับแล้วมีผลกระทบต่อ 14% ของผลิตภัณฑ์มวลรวมโลกนะครับกระทบต่อระบบสาธารณูปโภคที่สำคัญของประเทศนะครับแหล่งมรดกทางวัฒนธรรมถัดมาก็จะเป็นในเรื่องของการตัดสินใจในการบริหารจัดการเนี่ยก็จะใช้เวลามากกว่า10 ปีนะครับกว่าจะถึงศตวรรษนั้นนะครับโดยเฉพาะ AR6 เนี่ยก็จะมีการจัดทำในส่วนของตัวขับเคลื่อนผลกระทบจากภูมิอากาศชายฝั่งหรือว่า CIDS นะครับซึ่งทางประเทศไทยเนี่ยก็กำลังมีการดำเนินการในส่วนนี้อยู่เหมือนกันนะครับโดยเฉพาะในเรื่องของการเพิ่มขึ้นของระดับน้ำทะเลสัมพัทธ์นะครับน้ำท่วมชายฝั่งการกัดเซาะชายฝั่งนะครับถัดมาก็จะเป็นการพูดถึงว่าตัวขับเคลื่อนผลกระทบ33ตัวในแต่ละภูมิภาคเนี่ยก็จะมีทั้งหมด9ภูมิภาคด้วยกันนะครับก็เริ่มตั้งแต่ภูมิภาคแอฟริกาเอเชียนะครับออสเตรเลียเอเชียกลางและเอเชียใต้ยุโรปอเมริกาเหนือเกาะเล็กๆมหาสมุทรเปิดนะครับมหาสมุทรเล็กๆมหาสมุทรลึกนะครับแล้วก็บริเวณขั้วโลกนะครับแล้วก็มีการสรุปว่าน้ำท่วมชายฝั่งเนี่ยก็จะเป็นตัวขับเคลื่อนผลกระทบจากการเปลี่ยนแปลงภูมิอากาศที่มีความเชื่อมั่นสูงนะครับแล้วก็ช่วงท้ายนะครับก็จะเป็นการสรุปว่าระดับน้ำทะเลทั่วโลกเนี่ยที่เกิดขึ้น1 ใน 100 ปีคาดว่าจะมีโอกาสเกิดหลายครั้งต่อปีภายใต้กรณี RCP 8.5 นะครับในกรณีที่เป็น RCP 4.5 นะครับคาดว่าจะเป็นเหตุการณ์ที่จะเกิด1 ใน 1 ใน 5 ปีนะครับสุดท้ายก็มีการสรุปว่าการคาดการณ์เนี่ยมีการคาดการณ์อยู่2แบบก็คือคาดการณ์ตามเซนาริโอต่างๆหรือ RCP หรือ SSP นะครับก็จะเกี่ยวข้องกับถ้าเป็นกรณีที่คาดการณ์ตามเซนาริโอก็จะเป็นเครื่องมือที่ใช้ในการปรับตัวนะครับส่วนการพยากรณ์หรือคาดการณ์โดยอุณหภูมิที่เปลี่ยนแปลงที่จะเพิ่มขึ้นเนี่ยก็จะไปช่วยในส่วนของการบรรเทาปัญหาหรือว่า mitigation นะครับเช่นเดียวกับการปรับตัวครับสำหรับผมก็ขอสรุปคร่าวๆเพียงเท่านี้ครับก็อยากส่งต่อให้ทางดร.ปิยมานครับ
ค่ะขอบคุณมากค่ะ Professor Roche ก็ได้โชว์เดโมตัวหน้าเว็บไซต์นะคะซึ่งได้แสดงภาพ projection ของผลกระทบของ climate change ที่มีต่อพื้นที่ชายฝั่งนะคะแล้วก็ระดับน้ำทะเลโดยแบ่งออกเป็น 5 ด้านนะคะเว็บไซต์ชื่อ coastal-futures.org นะคะทุกท่านลองเข้าไปดูได้นะคะซึ่งสามารถดูผลกระทบ 5 ด้านก็คือมีด้านระดับน้ำทะเลที่เปลี่ยนแปลงนะคะระดับน้ำทะเลสุดขั้วนะคะน้ำท่วมชายฝั่งแล้วก็มีเรื่องของ shoreline change นะคะการเปลี่ยนแปลงเส้นชายฝั่งแล้วก็สุดท้ายจะเป็นเรื่องของ extreme wave นะคะคือเรื่องของคลื่นนะคะทุกท่านสามารถลองเข้าไปดูได้นะคะซึ่งสามารถซูมดูในบริเวณพื้นที่ชายฝั่งประเทศไทยได้ด้วยเช่นเดียวกันค่ะในการบรรยายส่วนที่2นะคะโดยคุณขินนั้นก็เป็นการแสดงผลการศึกษาโดยการทำการ projection ของระดับน้ำทะเลสุดขั้วที่มีผลต่อชายฝั่งภาคใต้ของประเทศไทยนะคะโดยวิธีการศึกษานั้นก็ได้ follow ตัวpaper นะคะที่ได้รับการตีพิมพ์ในวารสาร Nature Climate Change นะคะหัวข้อ Extreme Sea Levels at Different Global Warming Levels นะคะโดยมีการนำข้อมูลแล้วก็ระดับตัว3ชุดข้อมูล ESL นะคะก็คือตัว Extreme Sea Level แล้วก็ตัวทำการแบ่งชุดข้อมูลเป็น2เซตนะคะโดยที่มีการโฟกัสที่ระดับ100 ปี Return Period และแบ่งเป็น3 Scenario ของช่วงอุณหภูมิ Global Warming Scenario นะคะซึ่งในการจัดทำ Scenario นั้นก็มีการพิจารณานะคะแบ่งเป็นในด้านอุณหภูมิมี 1.5 3 และ 5 องศาเซลเซียสนะคะซึ่งที่มา 1.5 ก็คือมาจากข้อตกลงปารีสในปี 2015 ซึ่งเป็นข้อตกลงที่จะป้องกันไม่ให้อุณหภูมิโลกนะคะเพิ่มเกิน 1.5 องศาเพื่อลดผลกระทบของ climate change นะคะส่วน 3 องศาก็เป็นแนวโน้มจากสภาพภูมิอากาศในปัจจุบันที่จะแตะที่ 3 องศาและ 5 องศาเป็นกรณีของ extreme level นะคะแล้วก็พิจารณาที่ return period ต่างๆคือ 1, 10, 50, 100 และ 200 ปีค่ะคุณขินเองก็ได้ให้ความสำคัญกับเรื่องของความเข้าใจคำว่า return period หรือว่ารอบปีการเกิดหรือว่าหลายท่านอาจจะใช้คำว่าคาบอุบัตินะคะว่าเป็นการอธิบายช่วงเวลาที่เหตุการณ์นั้นๆมีโอกาสที่จะเกิดขึ้นนะคะซึ่งมีการยกตัวอย่างเช่นกรณี100 ปี Return Period ก็มีโอกาสที่จะเกิดขึ้น 1% แต่สามารถเกิดขึ้นในปีใดก็ได้ก็ในแต่ละปีนะคะก็คือ any year การเลือก Scenario ของ Return Period นั้นก็มีหลักการก็คือว่า1และ10 ปีก็เป็นไปตามเกณฑ์การออกแบบการบริหารจัดการชายฝั่งและการกัดเซาะที่50 ปีจะเป็นเกณฑ์ที่ใช้ในการออกแบบท่าเรือ100 ปีเป็นการออกแบบระยะถอยร่นเพื่อกำกับการใช้ประโยชน์ที่ดินชายฝั่งและที่200 ปีก็เป็นการนำไปใช้ในเรื่องของประกันภัยนะคะทั้งนี้ก็เพื่อให้เกิดการวิเคราะห์ที่ practical และสามารถนำไปสู่การปรับใช้ได้จริงนะคะผลการศึกษาได้มีการเปรียบเทียบผลกระทบกับพื้นที่ชายฝั่งประเทศไทยทั้งหมด8พื้นที่นะคะแบ่งเป็นอ่าวไทยตอนบนไล่จากทางฝั่งตะวันออกจะมีจังหวัดจันทบุรีระยองชลบุรีสมุทรปราการเพชรบุรีนะคะอ่าวไทยตอนล่างสุราษฎร์ธานีและสงขลาและฝั่งอันดามัน1พื้นที่คือที่ภูเก็ตนะคะสรุปผลกระทบของการเพิ่มขึ้นของระดับน้ำทะเลก็ได้มีการพิจารณาเป็น3ช่วงเนื่องจากว่าการโปรเจกต์ไปในระยะยาวมันจะมีความไม่แน่นอนค่อนข้างสูงนะคะก็จะมีการพิจารณาซีนาริโอที่แย่ที่สุดปานกลางแล้วก็ดีที่สุดนะคะโดยผลการศึกษาก็พบว่าที่ซีนาริโอของ global warming level ที่ 1.5 องศานะคะ นะคะ percent change เนี่ยจะเพิ่มขึ้นอยู่ระหว่าง 20-180% นะคะ3 องศา 50-350% และ 5 องศาคือกรณีที่ extreme ที่สุด percent change เนี่ยก็จะเพิ่มขึ้นถึง 50-500% ค่ะสำหรับระดับน้ำทะเลที่เพิ่มสูงขึ้นนี้นะคะก็จะเห็นได้ชัดเจนในรอบปีการเกิดที่1และ10ปีก็คือ low impact แต่ high frequency นะคะก็คือผลกระทบอาจจะยังไม่ได้สูงมากแต่ว่าเกิดขึ้นถี่และบ่อยมากกว่ารอบปีการเกิดอื่นและการเปลี่ยนแปลงชายฝั่งเนี่ยจะเห็นชัดเจนที่ global warming level ตั้งแต่3 องศาขึ้นไปโดยแนวโน้มการเกิดการเปลี่ยนแปลงของชายฝั่งประเทศไทยก็เป็นไปในทิศทางเดียวกันและมีผลกระทบกับชายฝั่งตอนล่างมากกว่าบริเวณอ่าวไทยตอนบนโดยเฉพาะที่ภูเก็ตและสงขลาซึ่ง sensitive to global warming level นะคะตามที่ทางคุณขินได้อธิบายเมื่อสักครู่นี้ในตอนท้ายนะคะ Professor Ross ได้ให้ข้อเสนอแนะว่าหากจะศึกษาผลกระทบกับชายฝั่งประเทศไทยให้มีความละเอียดและถูกต้องกับสภาพพื้นที่นั้นก็จำเป็นที่จะต้องมีการทำ ensemble downscaling โดยเลือกตัว global โมเดลที่มีความเหมาะสมกับประเทศไทยนะคะและสิ่งที่สำคัญก็คือการพัฒนาแบบจำลองน้ำท่วมชายฝั่งที่จะต้องมีรายละเอียดข้อมูลภูมิประเทศหรือว่า DEM นะคะที่มีรายละเอียดสูงสามารถครอบคลุมรายละเอียดของโครงสร้างการป้องกันชายฝั่งด้วยนะคะโดยได้แนะนำตัวแบบจำลองที่ชื่อว่า Sphinx นะคะหรือว่า Super Fast Inundation of Coast ซึ่งแบบจำลอง Sphinx ตัวนี้เป็นแบบจำลองน้ำท่วมแบบองค์รวมนะคะที่สามารถ optimize เพื่อเพิ่มประสิทธิภาพการคำนวณได้สูงสุดลดความซับซ้อนของแบบจำลองเพื่อให้สามารถคำนวณได้รวดเร็วนะคะแต่ยังคงความแม่นยำเอาไว้ได้ซึ่งแบบจำลองตัวนี้นะคะก็จะสามารถทำให้เราจำลองพื้นที่น้ำท่วมชายฝั่งได้อย่างถูกต้องและแม่นยำแล้วก็นำไปใช้ในเรื่องของการศึกษาความเสี่ยงทำพื้นที่แผนที่เสี่ยงการควบคุมการประโยชน์การใช้ที่ดินชายฝั่งนะคะรวมถึงการออกแบบมาตรการต่างๆเพื่อป้องกันชายฝั่งได้อย่างแม่นยำมากขึ้นค่ะก็ขอสรุปการบรรยายในภาคภาษาไทยเพียงเท่านี้นะคะเดี๋ยวส่งคืนให้ทาง MC ค่ะขอบคุณค่ะ
ขอบคุณค่ะ
ขอบคุณครับ
Thank you very much Dr. Piyaman and Dr. Vinay ค่ะ Next may I hand this floor for the Q&A session If any participants would like to ask the question or share your experience, please feel free to ask the question and share your idea. ทุกท่านคะช่วงนี้จะเปิดโอกาสให้ทุกท่านนะคะได้ถามคำถามสำหรับการบรรยายในวันนี้ค่ะหากท่านใดมีประสบการณ์เพิ่มเติมค่ะสามารถแชร์ได้ค่ะก็ค่ะดิฉันขอเปิดโอกาสให้ทุกท่านณบัดนี้ค่ะ Please welcomeมีคำถามจากท่านใดไหมคะด้านหลังค่ะ
Hi, good afternoon. Thank you very much for your great presentation. My name is Thanat Pong from Faculty of Fishery, Department of Marine Science. I'm a physical oceanographer. I have two questions. First, I know doing the numerical simulation is kind of estimation, but do you have some sort of validation or calibration of the model, especially in our water? That is the first question. The second question is very interesting to see that the southern part of Thailand, Songkhla and Phuket, have more influence on the estimate extreme sea level. I can see that your extreme sea level is come from tide, storm surge, wave setup, and sea level. What contribute most? Which one is the most contribution of that? Thank you.
Thank you so much for your questions, and it's a quite interesting question. And to address your first questions, that we do some calibrations and validations of our results. And actually, we combined the present day extreme sea level data sets. We have 3 data sets. And all these data, but two data sets came from numerical modelings, and one data set came from observations, reconstructions. So, but unfortunately for Thailand, we don't have observational data, so we only use two data sets, which comes from the model. And these data sets are already published online, publicly published, and they also already calibrated and validated in their papers. And we use these two data sets, and again, we combine that present day data sets with future sea level rise projections. And these two data sets also published and calibrated and validated. And what we did is we just take this extreme sea level data sets of present day, and we pick up randomly from the relative sea level change distributions. And we also produce different samples, a lot of samples, over 1,000, by using Monte Carlo simulations to really capture the uncertainties, because we are projecting for the future. And yeah, this is the answer from me for your first question. Are you satisfied with the answer? Okay, and then we can move on to the second questions. And I already forget what your question is.
You said that Songkhla and
Yes.
are more vulnerable for this change.
Yeah. Now I remember. Yeah, and as Professor Roche mentioned before, for extreme sea level, we have contributions from storm surge, tide, relative sea level rise, and wave setup. And in present day extreme sea level data sets, we consider, these in their models to develop these present day extreme sea levels, it is already considered that the storm surge and tide and also the wave setup in their models. And we combine that present day extreme sea level with relative sea level change in the future. So, meaning that these increases are very large in Phuket and Songkhla in the future. It's only because, not only, it's a very strong word to use, we think relative sea level change is dominant in these regions. That's why we have such sensitivity, because we base our methodology by combine relative sea level change. Did I answer?
But
Yeah.
just to be more specific, have
Yes.
you ever have chance to look into, for example, wave setup contribute more, or
Mhm.
storm surge contribute more, or sea level rise contribute more? I know that it's a very detailed, because
Yes.
you consider the whole Earth. But
Yes.
just in case you already have a look into that, we are interested to know which one contribute more.
Yeah, it would be actually a good research to really look into which part is contributing more. But in our result, we didn't include the contribution from how the cyclones will change in the future. We don't have such kind of information to include in our current study. Yeah, thank you.
Okay, please move to the next question. เดี๋ยวรบกวนขอโทษนะคะ ก่อนถามคำถาม
So sorry.
ค่ะจะรบกวนให้ช่วยแนะนำตัวเองนิดนึงค่ะ
โอ
ว่า
เคครับ
ชื่ออะไรมาจากหน่วยงานไหนนะคะ
ครับผม
ขอบคุณค่ะ
So thank you very much, Professor Ross, and also Ms. Kins, for a very informative presentation. So I'm Kitanai Tosi. I've been working for Hydroinformatics Division. And actually, my background is not related to the causal and the marine science, but my background is related to meteorology and climate variability. So I just wonder that because I have heard one term
that called meteorological tsunami something, right? Is there any difference or the same as the extreme sea level rise here? Is it the same term? Or meteorological tsunami, right?
Did I press a button or something? This automatically. Yeah, well, I think this is very different. Extreme sea level is very different to meteorological tsunami. But I'm not an expert on meteorological tsunami. I have also seen this word, but I mean, I haven't come across that term as a synonym for what we call extreme sea levels. So I think they are different animals.
Okay, thank you very much. So another question, maybe last question, because of according to your presentation, IPCC have a very high confidence that we can have sea level rise. Maybe we already have some evidence from the historical record and also from the maybe zero climate projection, right? We're gonna have very high sea level rise in future, and also from Ms. Kin that over Thailand, we're gonna have, the change in the sea level rise in the coastal area. So, according to your experience, do you have any, idea or opinion that how could we bring this information to the community to aware of this phenomena in the future?
Yeah, well, that's a good question, to which I think I don't have a very good answer. But I think communication of scientific research is a very challenging task. It's not to be underestimated. Few times I have tried to do that. You just realize how much technical jargon that you use. You know, when we normally speak, you use words thinking that everyone else understands it. Like acceleration has a specific meaning to us, and exacerbation has a specific meaning to us. Even the word specific. But if you talk to local fishermen, you have to tone things down quite a lot. So I think, but it is really important because now more and more, I think Sutta and I were also talking about it at lunch, decisions, like, I don't know, 50 years ago, decisions could be made top down, like engineers and planners and policymakers could decide, okay, this is the hazard, we don't want to, this is the hazard level that we can accommodate. And beyond that, we are not going to accommodate, we have to do some protective measures. And then you decide on the protective measure, you go and build it. You get money from the government, go and build it, and tell the people afterwards, this is why we, but now it's completely different. Now it starts from the community. Things have to be agreed by the community and local stakeholders, and that's when you get the money from the government to do the work. So educating people and not talking to people in a language they understand is extremely important, and I think we have to engage the help of specialized groups who can do that. There are specialist communicators, but we can then also tone down our scientific findings in such a way that the communicators can understand. I'll give you a little example that I went through recently. We got a small amount of funding from an insurance company called AXA to produce an outreach product on how climate change would affect coastal zones. So we have the technical knowledge. So we made some cool, simple-looking graphics and put it in a nice brochure. And then we asked the representatives from the insurance company to give their feedback on it. So a very knowledgeable communicator was the one who was our main liaison. And in our figures, we had several situations or several things, several climatic changes that could happen that would affect tidal inlets. The inlets could be closed or migrated, or they were closed ones would open. You can imagine, like Songkhla Lagoon, if the inlet closes, there will be serious consequences. We know that. But when we showed it to this person, this French lady, she doesn't know anything about coastal stuff, right? So she asks a very good question. So to who does it matter that this little channel closes, Why does it matter? So to us, this is like, it should be obvious, but to general public, it is not so obvious. So that's why it's important to work with specialist communicators to get these messages across. I think it's very important.
Thank you, Mr. Kitanai. Next question, please. Anyone would like to share your experience? Your experience is welcome. Okay. Please. Please introduce yourself first.
ผมนะครับเดี๋ยวคนไหนข้างหน้าเอาผมก่อนโอเค Hello I'm Suryan Saramoon from Chulalongkorn University I have a question since you got the funding from the insurance company so about the result from Kin I'm curious why we don't see the extreme sea level in the upper Gulf. So maybe you didn't include the anthropogenic effect from like land subsidence or something, because in the upper Gulf we have this problem. So my question is it possible to include such a effect to your model?
Thank you for your questions. And as when we say relative sea level change, we also consider the how it is relative to the sea level at each location. But our assessment is very global, so I don't think we can go really details of land subsidence, how much, for example, for the upper part of the, along the coastline of the Gulf of Thailand. So if we have such kind of local level detailed information, I think we can really integrate that into the relative sea level change estimates, and then we can project it against the extreme sea levels. Does that answer your question? Thank you.
Please. แนะนำตัวเองนิดนึงนะคะ
Thank you for your presentation. My name is Balang Miengpo from Marine Department. Actually, my question is related to the previous question about the meaning of the ESL. The ESL is the term of Thai storm surge, wave setup, and sea level rise summed together. Well, I just want to know that is that just a sea level rise or a relative sea level rise? And Ms. Kin already answered. Because in Thailand, we have a problem of land subsidized. And also in Jakarta, a lot of land subsidized and make the sea level rise very, very quick. Well, Ms. Kin already answered that we don't take into account the land subsidized for this study. Maybe in the future, we can take into account this, and it will be more useful for Thailand. Thank you.
If I may comment on that, actually, so for previous assessment reports, really the subsidence effect was not included at all. But in this assessment report, we specifically report on this relative sea level rise, right? So the subsidence effect is included in the relative sea level rise projection in as much as it can be captured by the global tide gauge network. If it's reported at a tide gauge network near your location, then it probably is included, but not beyond that. Okay, so we don't have global maps of subsidence. But I don't think in the Gulf of Thailand there is such tide gauge that captures subsidence. But if there is information like that available to you locally, my suggestion is to really publish it somewhere, because then it gets, then we capture it in our big netting that we do for the next assessment reports.
Thank you for your question. Is there any question so far? Okay, please.
It's me again, Thanat Pong from Department of Marine Science, Kasetsat University. Actually, Dr. Suryan, you published a paper, right, about the relative sea level rise, and also the data is from the tidal gauge. So the data is available. I think Dr. Suryan can really answer this. There is another thing. This is not a question but suggestion. In the Gulf of Thailand, we have been influenced, like you said, sir, have been influenced by monsoon. We have so-called seasonal sea level cycle. When we have northeast monsoon, our sea level rise. When we have southwest monsoon, our sea level drop. And this also depends on those El Nino, La Nina, ENSO, and IOD. Sometimes we have very extreme northeast monsoon. So our level really go up high. So in case if you want to continue the study, downscale, you should include this seasonal sea level cycle in the model in the Gulf of Thailand. But maybe not in the Andaman Sea. Andaman Sea is not that much difference. But in the Gulf of Thailand, it is as high as 40 centimeters. 40 centimeters, yeah, the magnitude of it. Yeah. Thank you.
Thank you very much for that suggestion. Take it on board.
Okay. Is there any question? Okay, so there is no further question. Thank you very much for all intensive question and answers from all participants. Okay, next, I would like to invite Dr. Suthat Risakun, Director of HII, to thank you for today's special lecture. Please welcome. รบกวนอาจารย์เชิญด้านหน้าเวทีนิดนึงนะคะ
ยืนพูดตรงนี้
อ๋อได้ค่ะได้
มีอยากจะพูดเพิ่ม before I say thank you to you just a little bit จากดร.ธนัทพงศ์นะฮะที่บอกว่าสงขลาเนี่ยสูงสุดเทียบกับภูเก็ตนะฮะเป็นแค่2ที่ใน8ที่ที่เขาเลือกว่าเขาไม่ได้เลือกทุกจังหวัดในงาน Research Limit 5เนี่ยยิ่งนราธิวาสปัตตานีเนี่ยมันจะเพิ่มขึ้นดีไซน์เวฟไฟเพิ่มขึ้นประมาณ 30-40% จะเป็น Limit 5นะจะมีผลถึงภาคใต้ของประเทศเยอะนะครับแล้วก็เหตุผลวันนี้ที่เชิญแล้วก็มีหน่วยงานที่กรมขอบคุณกรมเจ้าท่านะครับกรมทรัพยากรทางทะเลชายฝั่งนะครับแล้วก็สผ.มาเพราะว่าเราดูตัวอย่างของกลุ่มที่โรสทำเนี่ยของเขา167คนนะฮะแล้วก็อีก500กว่า contribution ประเทศเราถ้าหากว่าประเทศไทยถ้าทิ้งให้หน่วยงานเดียวทำเนี่ยไม่รอดเขาก็จะคิดว่าเป็นงานของหน่วยงานไม่ใช่งานของประเทศนะฮะแต่สสน.ก็พยายามขอบัดเจ็ตนะแต่คงจะไม่ได้ คงจะไม่ได้ก็พยายามทำต่อยอดจากฐานที่มีอยู่แล้วก้าวเป็นก้าวที่3ก้าวที่4ไม่ได้ก้าวจากก้าวที่0นะครับถ้าไม่ได้ก็ไม่เป็นไรเพราะว่า Sea Level Rise เป็น100 ปีก็ขอไปเรื่อยๆโอเค ก็ดูความพยายามของเราขอไปเรื่อยๆที่ต้องขอบคุณหน่วยงาน เพราะว่าถึงเวลาแล้วฮะที่ต้องเริ่มการทำงานแบบใหม่ ซึ่งทาง IPTC เนี่ยเห็นได้ชัดที่โรชบอกว่าจากท็อปดาวน์เนี่ยเป็น bottom up จากคอมมูนิตี้ขึ้นมาถ้าประเทศเราประเทศไทยนะฮะถ้าที่นี่เรายังไม่เปลี่ยนเนี่ยทำเหมือนเดิมโซลูชันก็จะได้เหมือนเดิมแล้วมันก็จะรีเซลจะเป็นเหมือนเดิมเพราะฉะนั้นในวันนี้ก็มีโอกาสดีนะฮะที่เชิญหน่วยงานมานะครับถ้าหากว่าอยากจะทำงานอะไรร่วมกันต่อไปสสยินดีนะครับที่ไม่ต้องใช้เงินหรือว่าใช้เงินที่มีอยู่แล้วนะฮะก็เริ่มทำงานด้วยกันอย่างเช่นมีคำถามว่า validation อย่างนี้หน่วยงานซึ่งมีข้อมูลอยู่แล้วก็ทำได้นะครับเรามีทีมเทคนิคคนที่ถามเนี่ยก็ไปช่วยทำได้นะครับเราช่วยกันทำเท่าที่ทำได้นะแล้วพอได้โครงขึ้นมาเนี่ยเราค่อยๆตบเข้ามานะซึ่งอันนี้เป็นหลักการของ empowerment ของชุมชนเราไม่ได้ท็อปดาวน์เพราะสั่งเราบางทีเราก็เถียงเราไม่เชื่อแต่ถ้าร่วมกันคิดร่วมกันทำไปเรื่อยๆเนี่ยความคิดที่แตกต่างก็จะรวมมาเป็นความคิดเดียวแล้วก็เป็นประโยชน์ให้กับประเทศของเราเพราะว่าอีก100 ปีประเทศไทยก็ยังเป็นประเทศไทยอยู่นะครับ so distinguished guests ladies and gentlemen it gives me great pleasure to extend my sincere thanks and appreciation to all of youที่มาร่วมในวันนี้นะครับในเรื่อง Extreme Sea Level for Thailand Lectures. The presentation was insightful and informative, which was an eye-opener for us all, highlighting and pressing issue of rising sea levels and their potential impact on Thailand. I would like to express my sincere appreciation to all of you who attend the lecture today. Your participation and engagement have contributed to the success of this event, and I hope we can all take the knowledge gained from this lecture and work together to address the challenges of rising sea levels, which should include coastal erosion and many consequences. CID, as you showed, that this is work just starting, just opening the floor. A lot of work should be conducted locally and regionally. Thank you again for your attendance, and I wish you all a pleasant evening. Thank you very much.
Thank you very much, Dr. Sukha.